This video gives my solution to the orange juice example. So here's the situation. We have three different brands of orange juice and three different time periods where we measure the vitamin C level in that orange juice. So what we did is we went off and we bought 4 cans of type C, 4 cans of type A, 4 cans of type B. We mixed up the orange juice and we immediately took a measure of how much acidity there was in each of our 12 containers of orange juice. Then what we did is we put all 12 containers into the refrigerator and let it sit for 3 days. We took them out 3 days, after 3 days, and measured all 12 of them. And then this plot is showing us the averages. We waited. We put them back in the refrigerator, waited it another 4 days, so 7 days in total. Took them out and measured it. And so what we want to do is understand how both the brand of the orange juice and how long it sits in the refrigerator affects the acidity level. So do they all lose their acidity at the same rate, or do some brands lose it faster than others? Okay, so that would be an interaction if we found that. So here's the data. You can copy and paste that into R. Let's go look at an interaction plot. So let's go do this live. So I'll go paste that, and we get our interaction plot. So that's exactly what you had in the course packet. So the question is there an interaction? And so remember that if the lines are parallel, we don't have an interaction. When the lines are not parallel, there is an interaction. So clearly these lines are not parallel, but 12 observations is not a very big sample size, and the deviations from being parallel could just be due to this particular sample. Okay, so that's why we need to do a statistical test to see if this is really just sampling variation, or are these lines really not parallel? All right, so we need to go fit a linear model. So let's go do that. So fit is equal to a linear model. We're going to predict acid as a function of time. We'll use the star operator. So time star brand, and our data frame is the OJ data frame. Now the first thing I want to do is look at a summary. Ordinarily, we wouldn't do summary first. We would do an ANOVA or a drop one, but we're just going to do a summary for now. The reason is I want to see what parameters have come into the model. So what we have is an intercept. We have 2 dummies for time, so it looks like the base time period is 0, and this is going to tell us what happens when we go from 0 to 3. This will tell us the difference between 0 and 7, time period 0, time period 7. So we have 2 time variables, 2 brand variables. So this is how brand B differs from the base category, which is A. This is how brand C differs from the base category, which again is A. Then we have 4 interaction terms. Now, I'd like to go over to my document camera here for a second and just write out what are the parameters. What are the parameters here? And this is going to be slightly tedious, but we need to establish our parameters. So you could say Y, you could say acid, whatever your dependent, however you want to express the dependent variable is up to you. I'll just say Y for now. And remember, I had an intercept. Then I'm going to say that I have a time effect. So what is T3? T3 is a dummy variable that takes the value 1 if time equals 3, 0 otherwise. So O period W period means otherwise. So if time period, so this would be time, oh, this is time 3. I messed that up. This is time 0 or 7. All right. So T3 is equal to 1 if the time period is 3, 0 otherwise. Then I have beta 2 times T7. What is T7? Well, T7 is equal to 1 if time is 7, 0 otherwise. Well, let's keep going here. Plus beta 3 times B. Well, what is B? B is a dummy variable that equals 1 if the brand is B, 0 otherwise, meaning A or C. Then we have another a brand effect, so beta 4 times C. C is equal to 1 if it's brand C, 0 otherwise. Then we have a couple interaction terms. So the interaction terms I'll call beta 5. And so I'm just going to go look at my R for a second. This was time 3 brand B, so T3B. So this is what happens when it's time 3 and you have brand B, otherwise you don't get to count beta 5. I got a beta 6, which, what is beta 6? It's times 7 times brand B, so T7 brand B. I have a beta 7, which will be T3 times C, and I have a beta 8, which will be times 7 brand C. So those are all the parameters in my model. All right, let's go back to R now. And I said that ordinarily you don't look at summary first. You do a drop 1 or you do an ANOVA. Let's go do a drop 1. So we'll do drop 1 on fit, and I'll say test equals F. And so what you'll see is that we have it's going to check whether it can drop any non-marginal terms. Okay, so what's a non-marginal term? It's something that doesn't have something underneath it. So time and brand both sit underneath the time-brand interaction. Therefore, we don't test those yet. So it's good practice. You don't test a main effect if you have an interaction. There's a reason for that. What is an interaction? An interaction is where the effect of one variable, say time, on the dependent variable, so acidity, depends on the other variable, brand. So therefore it doesn't make much sense to talk about a main effect if there's an interaction. That's why we're only testing for interactions at this point. So what exactly is being tested here? The key to understanding this is to look at the degrees of freedom. So we have 4 degrees of freedom. And so let's go back to my document camera, and I want to express what the null hypothesis is. So the null hypothesis here is beta 5 equals beta 6 equals beta 7 equals beta 8, all equals 0. So notice I've got 4 degrees of freedom, 4 betas, 4 parameters that I'm constraining to be 0. In English, there's no interaction. All right. The alternative is that at least one of these betas is non-zero. So J equal 5, 6, 7, or 8. In English, this means interaction. So, at least one of these is non-zero, which means the relationship depends on, the relationship between time and acidity depends on brand, or you can express it the other way as well. All right. So I'm not going to, let's just talk a little bit about what these numbers mean. So when I fit the model, the reduced model, where I've constrained all 4 of my parameters to be 0, the objective function increases by 17.3. All right, I could go off and compute the F statistic. So if I take 17.3, divide that by 4, so I'm going to go write that over here. So it was 17.3 divided by 4. Divide by the mean squared error. So what's the mean squared error? Well, we can get it from right here. So 3.07 squared. This is equal to 0.46. So 0.46. Now, we could go look this up in the F table. And so if you do that, you find the p-value is 0.76. So let me just write that. P-value is 0.76. One way to think about this is you have an F distribution out here. This is your F distribution. Somewhere out here is the value 0.76. This, or sorry, 0.46. The area to the right, so this whole area out here, is 0.76. All right, this is substantially greater than 5%. So we cannot reject H naught. So what this really means is we don't have evidence to say there's an interaction. Not enough evidence to say there is an interaction. So going back to R, we had this interaction plot. It's entirely plausible that these lines are parallel. It's just the sample that we have had some deviations from parallelness. All right, so what that means is we really shouldn't be looking at these parameters. None of them are significant, but there's a chance that some of these could have been significant. We shouldn't be looking at them at all until we've done this F test to conclude that at least one of these is non-zero. So we need a different model. So the different model we're going to fit is going to be very much like the old one, but we're going to put a plus sign in here. So we know there we can't really say there's an interaction. Therefore, let's go fit an additive model. And let's go look at our parameters. Now, again, you should do your F tests first, but I just want to point out that what we just did was we got rid of the 4 interaction terms with that. Let's go do our drop 1. So drop 1 on fit. Let's again get our F statistic. And so notice we have slightly different lines here. And so let's just let's go look at the brand line. And the question is, what does this brand line tell us? So what this tells us is, again, pay attention to your degrees of freedom. I'm going to go over to the document camera. And basically what we've done is we've dropped all of those terms. So we're just left with those 4 terms in the intercept. What the brand line is testing is whether we need these 2 terms, beta 3 and beta 4. Remember, there are 2 degrees of freedom. What this is really allowing for is a different, intercept, if you will. If it's brand B instead of brand A, this one allows for C to have a different intercept. So I can write that as follows: H naught beta 3 equals beta 4 equals 0. And so if we want to write what this means in English, I would say something like brands B and C are the same as the base brand, which is A. So, or you could also just say no brand effect. The alternative is that at least one of these, so you could say beta 3 is non-zero, at least one of these is non-zero, and or beta 4 is non-zero, which means that in English, either B or C is different from A, or both. Both could be different. Okay, so if both of these are non-zero, that means they're both different from A. If only one of them is non-zero, then one of them is different from A. All right, so if we go back to our output, this number right here says our objective function increases by 33 if you fit the the null model, where you constrain those two betas to be 0. The p-value is not significant, so I would say p is 0.17, which is greater than 5%, so we cannot reject h naught. So we don't really need the brand effect in this model. Just for completeness, let's go look at the other one. So what is this saying? The other one is saying you've got two time effects. So h naught is, if we go back and look at my sheet, do I need these time effects? By the way, we just decided we don't need these, so get rid of those terms. But what are we testing now? Well, beta 1 equals beta 2 equals 0. The alternative is that beta 1 is non-zero and or beta 2 is non-zero. So in English, this means acid does not change, A-N-G-E, gotta spell that right, over time. In English, this means acid level changes over time. All right, so when we go look at our output, notice our p-value is tiny. The objective function value would increase by 227. The fit is much worse, and it's significantly worse, so 0.000082. is your p-value. That's way less than 5%, so we're going to reject h naught. Now, at this point, I think I'm going to go fit another model. We don't really need brands, so what that test told us is there is no brand effect. All you need is a time effect. And if I do a summary on fit, or if I do a drop 1 on fit, doesn't matter. Notice the p-value here. So this is testing whether at least one of these is non-zero, is 1e to the minus 4th. That should exactly equal this number right here. So 0.0001 is 1e minus 4. Notice your F statistic is exactly the same because those two tests are equivalent to each other. So basically what I'm concluding here is there is a brand effect. Oh, sorry, not a brand effect, a time effect. And let's just go right out the equation here. So acid is 51.25 minus 4 times T3 minus 6 times T7. So I just wrote that out here. Might be kind of useful to graph this thing. So here's T. Here is your acid level. And so what it says is that at time 0, the average acid level is 51.25. If you wait 3 days, the acid level is going to drop by 4. So this value would be 51.25 minus 4, which would be, what is that, 47.25. If you wait 7 days, so let's go out here 7, it looks like the acid level drops by 6. So the difference between those two is 6. So 51.25 minus 6 would be 45.25. It's a 5 there. So notice we really have a nonlinear relationship. So there's a nonlinear relationship because if you go 3 days out, you lose 4 units of acid, while if you go another 4 days out, this just drops by another 2. So there's like diminishing returns on the amount of acid that you're losing, and so it would be a bad idea. Do not use a linear effect. So what I mean by that is do not do something like this: y equals beta naught plus beta 1 times time, where this time could be 0, 3, or 7. So this model would not fit, because what we found here is that there's actually a nonlinear effect. All right, I think that orange juice example was very rich in terms of all the content in there. So it's worth kind of watching this video twice if need be.